Hello everyone, welcome to this lecture video tutorial in the mathematics of the modern world. Enjoy learning. To find the range of this equation, remember that we have to write it in this form. X in terms of y. Okay, right. Okay, in this form, x in terms of y. So use symmetric property. We have this one, and then we have to square both sides. So we have x is equal to y squared. So as you have noticed here, you will be tempted to conclude that the range is the set of real numbers. So as you can see in the step, so we write the equation here as x in terms of y. Okay, the numerical coefficient is 1, the exponent is 1, and then all the y values are on the right hand side. Okay, so it says here that you have to determine the biggest set or largest set of values of y for which x is well defined. So you will be tempted to show that the range is the set of all real numbers, because for every y from negative infinity to positive infinity, you will get an x, okay, which is well defined. However, notice that in the original original equation, we have y is equal to square root of x. So what if you are tempted to so actually, if you look at the graph of this equation, the range is only from 0 to positive infinity. So let's have some samples. Okay, some let's say some sample values. Let's say if you have a y which is -1. Okay, so what will happen if you use -1? So we have substitute x is equal to -1 square, and then you evaluate. We have x is equal to 1. The square root of the square of -1 is 1. So you actually get a 1. However, if you substitute to the original, okay, so go to the original given. So if you go to the original given, y is equal to square root of x. So if you substitute your y here is -1 square root of x. So as you have noticed, you cannot find an x that gives the value -1. Okay, you cannot find an x. Okay, from here you will conclude that you cannot find an x that will give -1. Okay, so with this our y, when we choose y which is equal to -1, doesn't belong to the range. But you may be tempted to show or to write that the range is from -infinity to +infinity. So how are you going to know if if your answer is correct? So notice, if you go back to the graph of this problem, we have square root of x. Okay, we look at the graph. Okay, if you look at the graph, you will see that the the range is will start from 0, as you can see here, from 0 to positive infinity. Okay, so why is that? So since you graph the equation y is equal to square root of x to the Desmos graphing calculator. Okay, as I've said before, that the range is from this one. Okay, this is your range. No, the sorry, the domain. Okay, the domain is from, let's write this, the domain, sorry, we have to make a bigger, let's say, this one is blue. Okay, the domain is of this equation, y is equal to square root of x, is from 0 to positive infinity. As I've explained before, for all x in this in the domain, you can find a y. You see here, this is your y. Okay, so from here you will have that one. Okay, and so on and so forth. Okay, so actually, if you project your values, your value here in downward, you cannot find a graph here. There's no graph in this area. Okay, so it suggests that the what do you call this one, this the range will start from this one. Okay, this is our, these are all the values of your y. Okay, so this is our your range. Okay, these values, so meaning to say the range of this uh, equation, y is equal to square root of x, the range is from, again, from 0 to positive infinity. Okay, so that's uh, how you will visualize, or how you are going to get the range of this, of the equation. Okay, y is equal to square root of x. Our notation is, we have d sub, is it g or something, is it d sub r sub g? Okay, sorry, is it r sub g, r sub g. Let me go back to the to the presentation. Where's that? Sorry, where is problem number 2? G. Okay, we use the notation G, so therefore okay, therefore show this stuff. So therefore our notation is this one, d sub g, domain, and the range. Okay, so is this always the case for what do you call this one, for the, for this kind of equation, y is equal to square root of x? Let's try to add a for an further illustration. Let's try to add a, what they call this one, a constant. Okay, plus 3. Okay, so notice here in this equation, y is equal to square root of x plus 3. The domain, as you can see here, the domain uh, the domain is just the same as the previous one. This is the graph of the, this is the graph of y is equal to square root of x, but this one is y is equal to square root of x plus 3. Okay, the difference now is it have a constant. Okay, we have a translation actually. So what happened here is the domain. So if you try to project a value here, let's say this one, let's try another color, let's try red. Okay, you have to another point here, and if you project upward, okay, there is actually a y values. The same is true from this one, these points, all points here. So if you look at, you can always find a y. Okay, y is always well defined. So again, the domain of this equation is the same as that of y is equal to this equation y is equal to square root of x. However, the range is, we will start from this point. Okay, because other than that, this in these values, okay, in these values, okay, this is the domain. Sorry, I have to delete this one. Okay, in these values here, okay, this is the domain, but there's no these points here from 0 to this one, from 0 up to 3, these are not counted. Okay, these points here are not counted in this in in this equation. Okay, this equation, this one, uh, these points here are not counted. So the points, the y values that only counts will start from 3 up to positive infinity. So as you can see here, let's try, what happened, let's try blue. Okay, we'll start from here. Okay, these are the points upward. Okay, so it depends upon the equation. So if you know how to visualize it in the graph, how to locate the domain and the range, as I've mentioned before, it's easy. Just this is the other way, aside from what they call this one, aside from solving the equation algebraically to find the domain or the range. Just look at the graph of the equation and you will see that the range and the domain are very easy to locate or to understand. Okay, so that's for the what they call this one, that's for the finding the domain and the range, the range. Okay, so let's erase that one, let's erase this. Okay, so from this from this given, you can see that the range is not actually all the values of y. Okay, so careful, please be careful, just analyze. Okay, so for other values, like when y is equal to, let's say, 1 or 2 or 3 and so on and so forth, or between 1 and 2, or between 2 and 3, or between 0 and 1, or 0. Okay, you will find that, for example, if you have this one, x substitute, say 1 square, what happened here is you have x is equal to 1. Okay, so if you go back to your original equation, if your y is 1, then actually you can find an x that will give uh, a y value which is 1. Your x would be x is equal to 1, and you will get y is equal to 1. Okay, so meaning to say your y in the element of the range is truly an element of the range of this equation. Okay, so that's basically what happened. So therefore our range here is from 0 to positive infinity. Okay, you can verify that in the graph. Okay, for the other problem, sorry, let's use the black one. Our third equation is y is equal to, I guess we have 3x plus 2. Is it 3x plus 2? 3x plus 2 over 2x plus 5. Oh, what happened? 3 plus 5. So let me see it again. 3x plus 2 over 2x plus 5, so that I will not be mistaken as the uh, previous problem. This one, I was wrong in copying the the problem. Okay, so let's wait for the program to respond. Okay, yes, I am right. 3x plus 2 over 2x plus 5. Our domain is this one, set of real numbers except 5 over 2. So I guess I am right. Okay, so don't forget, in the previous discussion solution, this is to find the range, okay. Let me recall that the domain, is it d sub h? Okay, suppose. Okay, I forgot again. This is the set of all real numbers except negative 5 over 2. Okay, so let's go back again. I'm sorry, I think my memory is lost. H. Okay, it is h. So first is, let's write this given, write it in x in terms of y. Okay, so let's try to solve. So all the x's must be on the other side, and all the y's must be on the right hand side. So what we will do here is to cross multiply. So cross multiply, so we have y is equal to 2x plus 5, 3 times 3x plus 2. So your y here is over 1. So multiply 2xy, 2xy distribute, okay, plus 5y, 3x plus 2. And then transfer all or transpose all the x's on the other side. So we have this one, this, and also this. So minus 3x is equal to 2 minus 5y. Look at here. Okay, and then factor out x. So we have 2y minus 3, 2 minus 5y, and then divide both sides by 2y minus 3. So our x is of this form over 2y minus 3. Okay, so what happened here is that we write this as of this form. So this is now x in terms of y. Okay, so this equation, it has a denominator, so meaning to say we have to find the value of y for which this equation is well defined, or this expression on the right hand side is well defined. So what value of y will make this denominator 0? So all you have to do is to equate to 0. So 2y minus 3 is the same as in the process of in the codomain. So we have 2y is equal to 3. Divide both sides by 2, so y is equal to 3 halves. So therefore this is defined for all values of x, of y, except 3 over 2. So therefore the range is the set of all real numbers except 3 over 2. Okay, that's the range. So if you look at the if you look at the graph of this equation, then you will see that the range does not include 3 over 2. Okay, let's eliminate this equation. Let's try 3x plus 2 over 2x plus 5. Okay, am I right? 3x plus 2 over 2x plus 5. Okay, so look at the graph. Okay, so our domain says here that it includes negative 5 over 2. So if the domain is x, so write negative 5 over 2. Okay, look at the vertical line, the points, the graph never touches the line. X is equal to negative 5 over 2. Extend it to positive infinity, and extend here also from to negative infinity. So what happened? Where is 3 halves? Okay, so our range is our values of y. Okay, so 3 over 2. Okay, so did you see the blue line, the horizontal line? Okay, it never touches the graph. If you extend to positive infinity, extend again to negative infinity, so clearly 3 halves here is not part of the range. Okay, so we verified in the calculation that our range is truly indeed this set. Okay, so that's how you are going to find the range. So for the fourth one, our fourth equation, we have, where is that? Our fourth equation is x plus 2. Let me, sorry, let me write it first so that I will not be mistaken. Our function is big F. Okay, so let's copy it again here. Number 4 is y is equal to x plus 2 over x squared minus 3x plus 2. Okay, this is hard. Our solution, if you recall, what happened? Okay, I'm sorry that the program is not responding instantly. So recall our domain. This big capital F is the set of all real numbers except 1 and 2. Okay, so we have to write this as, right, to find the range. Okay, write it in x in terms of y. Okay, for our solution we have to cross multiply. So let's use the, sorry, you have to cross multiply. This is over 1, so we have y x squared minus 3x plus 2 is equal to x plus 2. Okay, x in terms of y. So we have x squared, y is equal to x squared minus 3yx plus 2y minus x minus 2 is equal to 0. Okay, and then we have to combine the x's. Y, this excess here, x, we have x here, minus let's see, positive negative of the quantity 3y minus 1 times x. Okay, plus 2y minus 2 is equal to 0. So from here, this is our A, this is our B, and this is our C. Okay, if you distribute this one, negative 3xy, then negative x. Okay, so that's probably the, okay, we have to write it in x in terms of y. So remember, as you can see here, why do we have to write it in this form? Remember that our goal is to write it in x in terms of y. The numerical coefficient of x is 1, the exponent is 1. So therefore, we have to, and also there is only one x here. So our goal in the right hand side is to write it in a single variable x. Okay, then all the y values must be on the right hand side. So from here, this is the formula. Okay, we have, do I have to write again the quadratic formula? So use quadratic formula. Okay, so let's write it again. For those students who forget, sorry, AC over 2A. Okay, 2A. So substitute. Our B is negative 3y minus 1 plus minus we have b is negative 3y minus 1 square minus 4a. A is y, c is 2y minus 2 over 2 times your a is y. Okay, simplify. This is really a complicated uh, equation, but don't worry, once we simplify it, then this will be nice at the end. 3y plus 1 plus minus square the first term, we have 9y squared, positive 6y square the last term is 1, minus distribute this one, this is 8y squared, and then negative, we have negative times negative, we have positive again 8, it's 8, okay, 8y, okay, over 2y. So let's wait for the app to reply. Okay, so let's simplify further. Plus minus, we have y squared, and then 9y squared minus 8y squared is combined like terms 8, we have 14y plus 1. Okay, we have to erase the excess over 2y. So let's analyze. Okay, notice that in this expression on the right hand side, there's no problem here. Okay, this first term of the numerator, there's no problem here, there's no existence of a radical expression, so this is true for all y. However, in this second term, we have a presence of a radical expression. Okay, so and the index is 2, so therefore the radicand, okay, inside of this sign symbol radical expression, the radicand is must be greater than or equal to 0. Why greater than or equal to 0? Because this is the index is 2. Okay, and also this is not this expression, this is not in the denominator, so it will include the y value, which is 0. Okay, because the square root of 0 is 0. Okay, so it must be that the radicand must be greater than or equal to 0. And of course, y must not be equal to 0. Okay, if we try to solve this inequality, we should take note that y must not be equal to 0, because in the denominator, if you get a y is equal to 0 from here, what will happen is that if you substitute y, the denominator becomes the whole expression becomes undefined. We have a 0 denominator, so we have to find to exclude y is equal to 0 here. So to solve this, again, this is really complicated. We have to factor. Can we factor this one? I guess by using factoring, it cannot be, That's why we use again quadratic formula. So we use quadratic formula repeatedly. So y is equal to, we will not write the formula of the quadratic formula, we write it before. So again, we have to solve for y, so our variable here is y. So negative 14 plus and minus 14 square, sorry, 14 square, b squared minus 4ac. Your a is 1, your c is 1 also. Okay, so what happened here is that the radicand is positive, so there's no problem. So we have to evaluate 14 square is 196 minus 1 minus 4. We have 192 over 2 is, can we simplify square root of 192? So the answer is, let's wait again for the program to respond. Sorry, we have negative 14 plus and minus 8 square root of 3 over 2. So let's further simplify. We have negative 7 plus minus 4 square root of 3. So our y values is this one. So our y is here is negative 7 plus 4 square root of 3, or y is equal to negative 7 minus 4 square root of 3. Let's convert this into a decimal form. Negative 7 plus 4 square root of 3. 4 square root of 3. Decimal is, as you can see here, negative 0.07179676972. How about the other one? Let's try to put minus. We have negative 13. This is negative 13.92820323. 928203323. Okay, so that's the value. Okay, so if we will use boundary equation, use boundary equation. This is in your algebra class. Okay, I don't know if your previous teacher know this method, but for this discussion I assume. So let's write it in the real line. We have negative infinity, negative, this one is negative 7 minus 4 square root of 3. This is bigger than this is smaller than this value here. Negative 7 plus 4 square root of 3. This is positive infinity. Our 0 is closer. This is our 0. Okay, sorry. Let's try a red color to let's let's wait for the program to respond. 0 here. This is closer to 0. So what we will do here is we have an interval. We have, sorry, let's wait again. That's the problem if you have a laptop is very slow to response. We have intervals. Let's say intervals. Let's write negative infinity to negative 7 minus 4 square root of 3, and then negative 7 minus 4 square root of 3 to 7 plus minus 4 square root of 3, and then negative 7 plus 4 square root of 3 to positive infinity. Okay, test points. Let's have this, our equation, y squared plus 14y plus 1. Okay, so you have to ask a question. Then conclusion. Okay. Let's wait again. Okay, our test points, you can have, we know that this value here is negative 13, so we have 15. We can get negative 15 as your test point. For this one, for this interval, you can have negative 1. Okay, for this you can have 0. 0 is not okay, you can have 0. It's just it is points. Okay, so if you substitute negative 15, is this greater than 0? Okay, negative 15 square times 14 times negative 15 plus 1, is this greater than 0? Okay, how about this one? Let's try 0 plus 14 times 0 plus 1, is this greater than 0? The answer is yes. So we have yes, no, yes. Okay, automatically, trust me. Okay, but if not, then you have to use a calculator. Just okay, so positive, then negative. Okay, no. Okay, so we have to choose. We have to choose this one, the yes portion. So our solution set is from negative infinity to negative 7 minus 4 square root of 3. Notice that we have to include y. I'll explain that later. Plus 4 square root of 3 positive infinity. Notice that at the end points, okay, at the end points here, at the end points, you will notice that this will become 0, because of course this is a root. Okay, this is a root of this equation. If you equate it to 0, this is a root, so therefore 0 must be greater than or equal to 0. So that's why we include the endpoints. The same is true for this value here. Okay, same is true. Okay, so and notice that 0 is included in this interval. Okay, 0 is here. Okay, so we have to be careful. 0 is inside, and please to remember that I write it before that y must not be that the zero value must not be included in the range, as you can see here. Okay, so this is now our, sorry, let's wait again for the program to respond. Okay, so many mosquitoes here. Okay, this is our range. Okay, don't forget, this is our range, R sub capital F. Okay, but we have to exclude. Okay, exclude exclude 0. Okay, exclude 0. So actually, if you want to write it formally, R sub F will be this set from negative infinity to negative 7 minus 4 square root of 3, sorry, union of negative 7 plus 4 square root of 3 positive infinity, excluding, no, not a set, excluding, we have to exclude 0. Okay, you have to exclude 0. Let's try to visualize our answer in the graph. Okay, so where is our graph? Our graph is, sorry, okay, our graph, okay, let's delete that equation. We have a new problem. X plus 2, x plus 2, x plus 2 over x squared minus 3x plus 2. Am I right? X squared minus 3x plus 2. Okay, enter. So as you can see here, just like before, this is our graph. Let's plot the domain, the vertical line, the value that is excluded in the domain. We have x is equal to, as you can see, 1. X is equal to 2 also. Okay, so as you can see here, that's two values, 1 and 2 are excluded in the domain. How about in the range? Our range is this one. This is what is the decimal value of this? From negative 0.070, negative 13. This is a negative 13.924. Okay, so let's zoom out. Okay, if we zoom out, notice okay, so I guess we have a nice result here. I think we have to include, this is, yes, I remember now. There are problems that, as you can see here, notice that in the simplified form, we write it as y in terms of x, and you notice that y is not included here. Okay, y is equal to 0 is not included here, and we are tempted to show that y is equal to 0 is not included in this equation. Okay, however, actually we have to go back to the what do you call this one, we have to go back to the original problem original problem. So just go back to the original problem. We have here, our problem is this one, okay. If you substitute 0 here, or y is equal to 0, can you find an x? Can you find an x? Let's say this is your domain. Sorry, let's hide this first. You have your domain here, and we have the codomain. Okay, using a diagram. So this is this is our domain. Okay, so can you is there, if your y is, if you have y is equal to 0, can you find an x here? Is there an x here that is mapped to 0? Okay, so that's one big question, because if you look at the graph, there is a, for, if you have an x is equal to 0 here, this one, let's use this. Okay, if you have a 0 here, notice that there is a point. If you extend the, okay, there's a point here, up here. Okay, you can find a point which is 2. Okay, so meaning to say, no, no, that no, not that one. Let's erase this. Okay, this is your y. Okay, remember that this is your y. This is your y. Sorry, we are now on the, on the range. Okay, this is your y. Y is equal to 0. Okay, can you find an x in the graph that maps to y is equal to 0? So actually there is this one. Okay, we have -2. Okay, so the partner of y is equal to 0 is the partner of -2 is y is equal to 0. Okay, and if you substitute, let's substitute to the, so when x is equal to -2, so we have here -2 plus 2 is 0, and there is, this is a number. If you substitute in the denominator, -2 square minus 2 is a number. Okay, 0 divided by a number is 0. So actually here is -2, this is -2. Okay, -2 is mapped to 0. Okay, so from here, I think, I'm pretty sure that the y is equal to 0 is included in the what they call this one, in the range. Okay, there is a cases like that. Okay, please don't forget. No, I have to erase this. Okay, here we have to show this stuff, hide. We have to include. Okay, so our analysis before is that since 0 is inside and we write y is not equal to 0, we have to exclude. Actually we have to include now. Okay, we have to include now, include 0, because, so let's again wait for the program to respond. Include 0 because include 0 because if you substitute to the original uh, given uh, y is equal to 0 has a partner, okay, has a partner which is x is equal to -2. Okay, so be careful, you have to be very careful, okay, in analyzing the range. Okay, so as you can see here, let's the range, okay, the range will start from what do you call this one, from -7 minus let me see again, -7 plus 4 square root of 3. What is this? Am I wrong again? What is -7? I guess this is let me negative, this is -13. Okay, then this is positive. Okay, this is -13. Okay, okay, so okay, I'm confused. Okay, sorry for that. So -7 plus 4 square root of 3. Let's try to, okay, sorry, what happened? Okay, move this one. Y is equal to -7 plus 4 square root of 3. Okay, am I right? 4 square root of 3. Yes. Okay, enter. So as you can see here, let's zoom in. Okay, so our range is from this one. Okay, it will start from this one upward. Okay, so we are correct. From -7 plus 4 square root of 3, which is in decimal form 0.00, that's 0.00, where's that one, 0.0717. okay, this one. Okay, so that's correct. So however, let's try to, as you can see, maybe in your eyes, okay, in your eyes, maybe you will see that the graph, the green graph, this one, green one, is touching the horizontal line. Y is equal to -7 plus 4 square root of 3. So let's zoom in. Okay, as you can see, it touches. Okay, but if you zoom in, okay, can you see that? Can you see that it never touches, even if you extend like this one? Okay, that's -7. Okay, seems like it touches, but never. Okay, look at. Okay, so let's go back to home. Okay, so it never touches. So we verify that our our range, this one, this part here is indeed the upper part or upper portion, okay, of the graph. This one, negative infinity to negative 7 minus 4 square root of 3, which is negative 13, negative 13 plus 0.9282032 If you look at the graph here, okay, this one, okay, the graph must start here, okay, that one, this is the vertex, and this must be negative 13 point is a 928, okay, as you can see here, 928, negative 13.928, okay. So it verifies, but let's try to plot that one. Negative 7 minus 4 square root of 3, okay. So can you see the blue one? Okay, let's try another color. Let's try orange. Can we pick orange? What happened? Can we pick orange? Okay, done. Can you see? Okay, that one, this is 13.928, negative 13, this one 0.928. So the from negative infinity, this is the, this will start the range, okay, downward, okay. So we have verified our result clearly. For so long, clearly our uh, based on the graph, we verify that our domain, our range is indeed this set. Okay, we have to erase this one. Okay, it's that one, and as you can see, it includes 0. Although in the equation, if you write the equation in terms of x in terms of y, we clearly note here that it should not be equal to 0. But based on the calculation and in the analysis, you will see that 0 is included. So be careful for that. There are times, okay, there are times that you will exclude or you will not include. It depends upon the equation. So as you can see here, we analyze this, the situation, and we see that that's really the case. Okay, so be careful. So let's start the last problem. You force me to do this, to have a very complicated given. Okay, for our last equation before we will end. Okay, before we end, what happened here? Let's wait for the program to respond. Lots of mosquitoes here. Where are you? Where are you? Let me copy the problem, this one. Okay, our problem is 3xy squared minus x squared plus 7 is equal to 0, and our function is h. Our domain is, where's the domain? Our domain is from negative square root of 7 to 0 union square root of 7 to positive infinity. So this is our range, our domain, sorry. Let's go back. Where are you? Okay, number 5. So let's rewrite again our problem. Our problem is 3x squared, 3xy squared minus x squared plus 7 is equal to 0. Okay, and if you recall, your domain is this one, square root of 7 union uh, square root of 7 to positive infinity. Okay, so we write the given as in x in terms of y because we are going to find the range. Okay, so finding the range x in terms of y, so we have x here, so we have to remain this. Oh, we have a quadratic, sorry, we have a quadratic, so therefore we have to use quadratic formula. So negative x squared plus 3y squared x plus 7 is equal to 0. Okay, our a here is negative 1, b is 3y squared, c is 7. So by quadratic formula we have xy, y in terms of x, sorry, is it y in terms of x? Where are you? For which x is well defined. Okay, sorry, so we are going to solve for y, so therefore this is easy. Okay, sorry. Okay, I thought we are going to find, let's erase this one. Sorry for that one. Okay, so we have to write it this way: 3xy squared is equal to x squared. What happened? Okay, wait, just wait. Let's wait for the program to respond. So sorry, I will write it again here. I'm confused. Okay, let's write it here. Okay, write in x in terms of y. Sorry, I was actually correct. No. I was actually correct before. We have x in terms of y, not y in terms of x. So therefore we have to use quadratic formula. So from here we have negative x squared plus 3y squared. So here our a is negative 1, b is 3y squared, our c is 7. So by quadratic formula we have x is equal to a negative 3y squared plus minus 3y squared minus 4 AC 4AC a negative 1, c is 7, 2 over negative 1. So we have negative 3y squared plus minus, we have 9y to the 4 plus 28 over negative 2. Okay, let's again wait for the program to respond. Let's move our minus sign here. So as you can see here at this portion, the first term, this is true for all values of y. So this is set of real numbers. Again, we have here a square root. Okay, we have a radical expression. The radical sign must be greater than or equal to 0 because also it is in the numerator. Our denominator doesn't have a variable. So from here we will get uh, 9y to the 4 plus 28 must be greater than or equal to 0. Solve for y. So our ops y to the 4 greater than negative 28. So divide both sides by 9. So y to the 4 must be greater than negative 28 over 9. Okay, as you can see here, if you take the fourth root both sides, and you will have, if you take the fourth root, or before that, notice that for all values of y from negative infinity to positive infinity, the expression on the left hand side is always greater than to this value, negative. This is negative. The if the negative number is raised to the power of 4, this is always positive here. That's why the values of y are all real numbers. But if you force to take the fourth root to get the fourth root both sides, again if you use your calculator, here is undefined. Okay, the right hand side is undefined. So this means that our range, okay, the values of y for which x is really defined is all real numbers. Okay, so from here the range of the function is all real numbers. So all real numbers. So let's look at the graph. Okay, let's look at the graph. Where are you? So if we look at the graph, if you remember your previous discussion, our y is this. We have two values. Am I right? Okay, let's wait for the program to respond. What happened? Let's look at again. Where are you? Where is our given before? Here. Okay, this one. This is, let me copy that one. Y is equal to plus minus square root of x squared minus 7 over 3x. Okay, so let's go back again. Where are you? Where are you? This one. Okay, so let me recall that our y is, this is for the graphing. Okay, x squared minus 7 over 3x. So let's graph this one. Okay, let's go back home and then delete all these values here. We have square root square root of the quantity x squared, let's see, minus 7 and 7 over 3x. Okay, so copy it again, and let's have a minus here, minus negative sign. Okay, this is the graph. Notice that our range is all values. Okay, so again, this is just the case in number 4. If notice that the notice that our, where is the domain? The domain is from negative infinity to 0. Negative in no, that's the negative square root of 7 to 0. Okay, this one to here, but not included 0. You cannot include 0 in the domain, and then also for these points here. Okay, and this is not included in the domain. However, in the range, our range is, it says here, the set of all real numbers. Okay, because 0 here, when x is equal to 0, if you substitute, if in the original x is equal to 0, we have, okay, there's no value because 7 is not equal to 0. But if you look at the graph, okay, if you look at the graph, let's go to show this stuff, this one. These are the values of the range, okay, upward, since it is a real number. Okay, and as you have noticed, when what do you call this one, when our x is negative square root of 7, okay, you have a y which is 0. Okay, so it includes, and also we have positive square root of 7 which is 0. Okay, so clearly if you look at the graph of the equation, our equation, clearly the range is from negative infinity up to positive infinity. Okay, as you can see here, negative infinity to positive infinity, all of these values here. Okay, all of these values. So our calculation is indeed correct. Okay, based on the graph. Okay, so that's it. That's how you are going to, I know it's a complicated, okay, the given are complicated, but it helps, it really helps if you know how to graph. If you have a graphing calculator, then it really helps in finding the domain and the range of the given function or relation defined by equations. Okay, so I hope that you learn something from this discussion. In the next topics, we will be discussing about properties of function. We will be discussing about onto one-to-one and onto function, uh, and then we will use that definition to know if the function, or if the function is has an inverse. Okay, so of course you can get the inverse of a relation, uh, but uh, in this discussion, we will get to make sure that the function is has an inverse which is also a function. Then you have to satisfy the two condition, one to one and on two. Okay, so for our next topic, that would be our discussion. Hello everyone. In this last topic, we will be discussing about how to find the inverse of a function. So if you actually ask me, why not inverse of a relation? Okay, so I will discuss that later, and probably will be able to analyze it after discussing this some scenarios. Okay, so actually it's very easy to find the inverse if you are given an ordered pairs. Okay, all you have to do is to interchange the coordinates. Okay, the abscissa becomes the ordinate and the ordinate becomes the abscissa, so all you have to do is to switch. Okay, that would be very what do you call this one, easy to to perform if the set of ordered pairs are finite, uh, maybe less than 20 or less than 50. That would be very much easy to handle. But if your uh, set of ordered pairs are more than 500 or more than 100, that would be troublesome. Okay, so all you have to do is to switch. Okay, that's for the ordered pairs. Okay, so notice here, let's have some scenarios. Okay, scenarios. Okay, uh, there are relations. Okay, there are relations that if you perform the inverse, okay, if you will get the inverse, okay, inverse, what happened is that it will also be a relation. Okay, it will also be a relations, and it could also be a function. Okay, so for example, if you have uh, the how about the quadratic example here, we have, let's have a quadratic equation where uh, let's have a quadratic equation for this one. Example, if you have this illustration, quadratic in y. Okay, so this is a simple example. Okay, this is a relation. Okay, because for every uh, for every, what they call this one, x values in the domain, you have two mappings in the codomain. So if you try to visualize this using what do you call this one, try to visualize this using a diagram. Okay, what happened? Copy and then paste. Copy and paste. So let's wait for the program to respond. Let's here, move it here. Okay, let's erase this one. Let's graph it first before the program to respond. You will have square root of y. Let's say x is equal to y squared. Can we graph this one? Y squared, this one. Okay. If you have this, okay, what happened? Let's wait for the program. For every points on the let's try to erase this. Okay, for every point, example, we have a 2 here. Let's try 4. Okay, this one, you have a point x. This is our x. There are 2 values of y here. Okay, this one. So meaning to say, if you try to I know now. I know what happened. Let's move it by using a cursor, not a mouse. Okay, that one. Okay, so what happened? What happened here is that this is our domain. Okay, the domain for this is, no, let's try another color. The domain is this set of all x is from 0 to positive infinity, whereas the range based on the graph is the set of real numbers. Okay, so notice that your number, your element 4 here is mapped to 2 values, which is positive 2 and negative 2. So as you can see here, not only that, okay, if you have 1, sorry, yeah, if you have 1, it is mapped to 2 values again, negative, positive 1 and negative 1, because you have to write this first as a as a y in terms of x. Okay, this will become y squared is equal to x, take the square root both sides, so y is equal to plus and minus the square root of x. So as you can see, if you put 4 here, we have 2 values. So as I've said before, if you describe it using a diagram, then you can transfer the equation using a diagram. You can visualize. What will happen is that if there are two arrows for every element here, or three arrows, or more than one arrow, what will happen is that the given becomes a relation. Okay, so if you define this what they call this one, if you define this equation, okay, let's say given uh, a mapping, let's say h, from the domain which is 0 to positive infinity to r, given by uh, x is equal to y squared. Okay, determine uh, if it is a relation or a function only. Okay, so all functions are relation. Okay, so from here we can say that this is a relation. There are what they call this one, properties of a function or relation, or the what they call it, a method. There is a method on how to to determine if the function, if the given equation is a relation or function, by using this test. Okay, so the test called vertical line test. Okay, vertical line test, vertical line line test. uh, this test this test is used to determine if the graph of the equation is a relation or not. Okay, what is the what do we mean by vertical line test? Okay, so let's uh, put it here. The vertical line test is a test where you are going to, what do you call this one, you are going to determine if the graph of the function is uh, a relation or not. Okay, so let me put it here. Where is that? Okay, that's this one. Okay, uh, the graph of a function uh, f mapping from this, you graph the function in the Cartesian plane. Okay, this is what it means. Intersects a given vertical line in the Cartesian plane at most once. Okay, so this means that in order for this test to succeed, then you have to graph. Okay, let's wait for the program to respond. You have to graph. If you don't have a graph, then this will not be applied. Okay, so for example, this equation x is equal to y squared, if you look at the graph, if you draw a vertical line, okay, let's erase this one. If you draw a vertical line here, this one, it touches the graph at most once. Okay, there are 2 points, so this is a vertical. This is what do we mean by a vertical line test. It touches the graph at most once. Okay, so meaning to say uh, that this equation is defines a relation. Okay, it is not a function. Okay, this is a relation. So okay, so however, if you interchange the rule of x and y, for example this one, if you interchange the rule of x and y, what will happen? It does the given equation becomes a relation, okay, or does it become a function or not a function or not a relation? Okay, so that would be a very interesting scenario. Okay, but analyze what I said. Okay, there are equations defined by there are relation defined by equation in which the inverse becomes relations or it becomes function, but there are also problems that it is not a it will not become a relation, it will not become a function also. Okay, the same is true for a function. Okay, for a given function, okay, if you get the inverse, it will also become a relation and it will become also a function. Okay, that would be very easy if you have to switch the coordinates if you define the functions using ordered pairs. Okay, but what we will do here is this scenario, this one. Okay, how to find the inverse of a function in which the inverse is also a function. Okay, so that would be a very interesting a question. Okay, so that will be our goal of this topic, the inverse of a function. Okay, so as I've said, uh, you cannot just what do you call this one, the ordered pair. You cannot just have do by switching. Okay, just like our example before. Let's try to visualize this. let's have an example, which is the case where if you have a relation, illustration here, in which the look at the okay, just look at this example, copy and then paste. Let's try to move it down, this one. Okay, let's have this scenario. So what if you have a domain and a codomain? So let's define this as this one, a function. Suppose this is a function. We have 1 2 3 4 5, and we have a b c d. So suppose that this is the mapping. Okay, okay, that one. This is a function. However, if you try to write this as a set of ordered pairs, this will become 1a, no, what if all you have to do is to switch? Okay, so in reverse, so what if the range, let's try to copy this one. Okay, let's paste another one. What happened? Copy again and then paste. Let's put it somewhere here. Suppose that you are going to switch this b a. Okay, so our a here, b c d, becomes like this. Okay, this is the illustration. Our a is mapped to 1, they are partners. Okay, our b is mapped to how many? 3 4 5, 3 4 5. Our c is 2. Okay, but based on our definition of the relation and the function, it says there that all of the elements in the domain must have a partner or a mapping, okay, or an image. So as you can see here, this illustrates that this is a function. This is a function, but this one is not a function nor a relation based on the definition. Okay, so we have to be careful from here, from this scenario, that there will become that there are given or problems in which you can have a situation where you're given a function and then the result will be a relation or function, or not a function, not a relation. Okay, relation. Okay, there will be a cases like that. Same is true for this scenario. Okay, you can have uh, not a relation, not a function. Okay, you can find a problem like that. Okay, but we have to be careful how the structure of the question is being stated. Okay, so just be careful. So I have illustrate, and I leave a problem here. This one, analyze if you are given a problem like this, can you actually uh, say that this is the inverse is a relation or a function the if you switch the domain and the codomain directly, can you actually get the what do you call this one, the inverse? Well, of course, the answer for this one is, not a relation. Why? If you switch A and B, if the domain now is R, for example, okay, if the domain now is R, then notice here there are values of x here. Remember that R is from negative infinity to positive infinity. This is defined only for all positive non-negative real numbers, okay, from 0 to positive infinity. So there are values in this set from negative infinity to 0, not including 0, that are not mapped in this in the in the in the domain. Okay, so I hope that this answers the scenario, this equation. Okay, so therefore we have to be careful in writing the question. uh, it will become troublesome later for for the student, or for the student to answer a question if it is not clearly stated, okay, in the question. Okay, so our goal here are based on the title. We have the inverse of the function. Okay, so remember, before I will proceed, the vertical line test is used only to determine if the given equation is a function or not. But you can use this if you have a graph. If you don't have a graph, then you cannot use this, because it's clearly say that the graph of a function or a relation. Okay, so be careful on how to use this. And based on our illustration before, uh, this is not the equation x is equal to y squared is not a relation. No, it's not a function, it is a relation. Okay, so how are you going to get the inverse of a function? Okay, so let me remind you again that the given must be a function, and how you are going to know that the relation, the inverse is also a relation. Okay, and by the way, the notation for the inverse is, if you are given a function f, then the inverse is denoted by the symbol. Okay, this is the given and this is the inverse. Okay, that's the inverse. Okay, so there are ways on how to, steps, should I say, there are steps that you should follow in order determine the inverse of a, or to find the inverse of the relation. Okay, so let's start here. If the given is in terms of ordered pairs, all you have to do is to interchange the coordinates. Okay, if the given is a diagram, all you have to do is to interchange. Okay, but what if the given is in terms of equations? Okay, so if the given is in terms of equation, then you have to use these steps or method. First is you are going to determine if the function is bijection. Okay, meaning to say it is one-to-one and onto. Okay, and then if first it is a function, of course. Okay, so meaning to say you are going to use the vertical line test. Okay, then the next one is you have to determine the if the given is one-to-one and onto. Okay, so steps in getting the inverse of a function. Okay, the first one is you have to know. Okay, you have to know if the function is one-to-one and onto. So determine if the function is one-to-one and onto. Okay, so by the way, in some books this is called injective. Okay, injective or injection. Okay, this term here is called surjective or surjection. And as a whole, so if it satisfies both, if the function is one-to-one or an onto, then it is called a bijection or bijective. Okay, depends upon how to use the statement. Okay, and then uh, after determining if the function is one-to-one and onto, then you are now ready to uh, get the inverse of the function. Okay, so we are now ready to get the inverse. So what you will do here is first is interchange the rule of x and y, then interchange the rule of x and y. The second is solve for y in terms of x, and after that the resulting answer will be your inverse. Okay, which will be denoted by uh, f inverse. Okay, so it should be denoted by f inverse. So these are the methods. Okay, but as you can see, what do we mean by one-to-one? What do we mean by onto? Okay, let's define it first. Let's wait for the program to respond. What happened? Really problematic. Okay, let's define first what do we mean by definition. This is the definition of the onto function. Okay, this is the definition. Remember before that the range of the function is the subset of the codomain. Okay, so recall that the range of the function is a subset of the codomain. So this is the definition of the onto. Let's have another color. Let's say let's try blue. If in case that the range R sub f is equal to the codomain, then your function f is onto. That would be easy. Okay, that would be easy for our definition of the one-to-one. Okay, this is the shortcut, the shorthand notation for the one-to-one function. For the one-to-one function, this is a way on how to show that the function is one-to-one. First is you are going to get all the values, let's say x and y. Let's wait for the program again to respond. What happened? For all values in the domain, okay, which is we denote as d sub f. Okay, if f of x is equal to f of y, then x is equal to y. Okay, this is how you are going to determine to prove or to show that the function is one-to-one. But there is a shortcut here, but you cannot use this as a formal, okay, shortcut. There is a shortcut use the horizontal line test. Okay, this test here, this is very useful, but it is not accepted as a what do you call this one, formal solution or proof to the given what do you call this one, if you are going to show that the function is one-to-one, you cannot use this as a formal solution, okay, or proof. Yeah, all you have to do is to use this definition, okay. But uh, if in case that you use this test, uh, all you have to do is you can use this as a counter example. Or if you look at the graph and then you you use this test, this is just the same as the vertical line test. If you use this test and then if it not satisfied by this test, then you can create a counter example that the equation uh, given is not one to one. Okay, so let's define this. The horizontal line test is defined as this way: a function is f is one to one if and only if every horizontal line intersect the graph uh, of the function at most once. Okay, so this test is the same as the vertical line test. So for the vertical line test, that test is used to determine if the graph is if the given equation is a function or a relation. This test here, the horizontal line test, is used to determine if the graph if the given equation is one to one or not. Okay, so the same at most once. So if you look at here, this equation x is equal to y squared, this is a one to one. Okay, this is a one-to-one what it was one this is a one-to-one uh, relation, because this is a relation. Okay, uh, can we use this test to show that for the function for the relation? So it says here that uh, the given must be a function. Okay, well, anyway, I will try to comment that later if you ask. Okay, I will try to search for it first. I'm not sure, but this test is used to determine if the given function is the graph is a function in the first place. And then it should be that uh, this test is used to determine if it is the graph of the function is one to one or not. Okay, so but you cannot use this in the solution. All you have to do is you can use this as a way to be sure that the given is uh, the given equation is not one to one or one to one. Okay, let's have an example before I will comment that one. So let's have an example here. Example uh, given uh, given what do you call this one, let's have given our previous problem. Okay, given f mapping from uh, mapping from define, and let's write it here. Did you remember your previous example, the quadratic equation y is equal to 3x squared? Okay, define by this one, f of x is equal to 3x squared minus x plus 2. Okay, can you remember this equation before? What we did is that, okay, what we did is that the domain for this equation is the set of real numbers, of course. Okay, this must be the set of real numbers mapping to the no, I guess the range must start from, if I remember it correctly, our range is from, can you look at the graph? Can we graph this one? I forgot. 3x squared, x squared minus x plus 2. Okay, this is 1.917. Is that from, is that 5 over, no, 5 over 2? I guess not. I think I have to recall it again. How did I did it? Where's the range? Sorry, where's that one? 3. Okay, 23 over 12. I'm sorry, that's 23 over 12. So the range, I did not write it here, sorry. The range, it's a good thing that I recall it. Okay, the range is r sub f from 23, starting from the vertex to positive infinity. It's good that we recall it. Okay, but anyway, it's 23 over 12. Where are you? Where's that one? Okay, 23 over 12. 23 over 12. to positive infinity. Okay, this is the, so as you can see here, how about the onto? Okay, so this is our, no, let's wait again for the program to respond. Based on our given, the range, the range is this set. Okay, 23/12 to positive infinity, and this is the the domain. No, this is the domain and this is the range, the codomain. Okay, so for the onto, let's say onto. Okay, since the range is equal to the codomain, then f is onto. Okay, that would be easy. Okay, based on the given. So be careful. Be careful with the given. There must be a something like this in the given to to know the codomain of the equation. Okay, so for the one to one, it says there at the top. Okay, you have to get the values, you have to pick a value from the domain and then uh, substitute it here and then show that it is x is equal to y. Okay, however, if you will use the vertical line test, here one, okay, vertical line test, let's delete this one so that you will not be confused. If you create a vertical line like y is equal to 4, let's say y is equal to 4, okay, this one, it touches the graph at most once. Okay, there are two values, so this means that this equation 3x squared minus x plus 2 is a what do you call this one, is a, is not one to one. Okay, so this equation, uh, this function defined by the equation y is equal to 3x squared minus x plus 2 is not one to one. Okay, this is not one to one. So by vertical line test, but again, you cannot use this test in the formal solution. So all you have to do is to verify it that it is not one to one. So what we will do here is to find a value that is equal, but the images are equal, but the points in the domain are not equal. Okay, so what is that value? Just one example. Okay, just one example, and then that will be the okay. Okay, so what is this value? 4. Okay, we have 4, so let's try 4. So let's based on the graph, based on the graph, uh, we need only only one example. Okay, this is what we call a counter example. And then to show that the function f is not one to one. now. uh, observe that f of as you can see here, f of 1, okay, not 4, okay, f of 1, as you can see here. Let's wait for the program to respond. What happened? It's loading. Okay, it's loading. So I hope that uh, the what I've written is not deleted. Where are you? Go back to, let's go back to what happened. Okay, we are almost there. This one. Okay, we have we try 1 and -1. Okay, notice if you substitute, this is our equation. Okay, oh, what happened? Is this equal 3 times -1 minus x minus -1 plus 2, 3 times 1 square minus 1 plus 2. Notice that the value is 3 plus 1 plus 2. This is 3, 4, 5, 6. What is this? 3. 3 minus plus 2. 3 minus 1. 3 minus 1, 4. 3 minus 1 is 2. Plus 2 is 4. Okay, sorry, what happened? What happened? What did I was wrong in choosing? Okay, sorry, we have, what should be the value? 4, 1. What is this? 1 is 4. What is this? Negative 0.667. Is that 0.667 is 2/3? Is it 2/3? Is that 2/3? 2 divided by 3 equals 0.667. It should be negative 2/3. Okay, it should be negative. So this is 1, 4. Okay, 1, 4. This is, so I guess I was wrong here. Square plus, what happened? 3 square. 1, 3 plus 1 minus 2. Okay, I was wrong in this. Sorry, I have to put a, sorry, it should be that this is on the other side. On the other side, this must be negative 2/3. Okay, 3 times negative 2/3 square minus negative 2/3 plus 2. So this will become, we have to cancel out, oh sorry, yes, let's use another color. We have to cancel 1. This will become positive 2/3 plus 2/3 plus 2. Am I right? No, this is 4. Sorry again. This is 4 since we square it. Okay, so get the LCD. 4 plus 2 plus 6. This will become 10 divided by 2 is 12. 10, 12 divided by 3 is 4. Okay, indeed they are equal. So notice that in the definition we have shown that f of x is equal to f of y, and then this is our assumption. Okay, this is our assumption, and we have to show that x must be equal to y. These two values here must be equal. However, if you look at this scenario, though the assumption, it satisfies that the assumption is true for this particular particular number, okay, 1 and negative 2/3. However, we have shown that in this case negative 1 is not equal to negative 2/3. Okay, so this is our x and this is our y. Based on the definition, it must be equal, but here they are not equal. So this implies that our f is not onto. Okay, so if you can find a point or points on the domain, okay, for which the definition fails, then automatically it is true for all values. Okay, for no, it's not true for all values, but I would rather say that if you can find one, then automatically the given equation is not a one-to-one function. Okay, so in this case we cannot get the inverse. Okay, so let's complete this. Find the inverse if it exists. Okay, so since from here, therefore f doesn't have an inverse. Okay, so let's have, okay, before that, why do we conclude it this way? In order for a function in order for the inverse of the function to exist, the function must be both one-to-one and onto. Okay, no, sorry, I'm mistaken again. This is one-to-one. Okay, I think I am so sleepy now. Okay, I made a lot of mistakes. Let's have another example. Let's try this one. Let's try this example to be, what they call this one, this example that the inverse will exist. Let's try the problem number number 3 before. If I remember it correctly, this is the given h. The function is h defined by this equation, h of x 3x plus 2 over 2x plus 5. Find h inverse if it exists. I guess the domain is set of all real numbers except negative 5 over 2, and we have to make the domain to be equal, the codomain to be equal to the range. This is a set of real numbers except may I look at the graph? 3x plus 2, 3x plus 2, 3x plus 2 over 2x plus 5. Enter. Okay, what is this value here? I cannot pinpoint. Let's recall. Sorry everyone. Sorry. Let's determine the, okay, this one, 3 halves. Okay, it's 3 halves. Let's go back. This one. Exact 3 halves. Okay, so let's have a solution. Okay, so we, in the last discussion, we determined the domain to be this one and the range to be this one. Okay, so we are done with that in the previous definition to show that it is onto, since the range f, no, h, r sub h is equal to r except 3 over 2. This is, you can find this in the previous problem or discussion, which is equal to, let's wait for the program to respond. It's almost 12. Okay, I guess I have to relax. Okay, it's equal to the codomain, then h is onto. Okay, how about for the one-to-one? So you have to get a value in the domain, which is set up for r real numbers except negative 5 over 2. Then compute h of x and h of y. So we are going to show that x is equal to y at the end. We are sure about this because if you look at the graph, if you draw a vertical line no, horizontal line. If you draw a horizontal line here, it touches the graph at most once. If you are not convinced with me, okay, this is clearly a function. If you draw a vertical line, let's try to draw a horizontal line. Okay, here. So imagine that this is a horizontal line. It touches the graph at most once. Okay, from here. Okay, so this is indeed a one-to-one function. Okay, unlike before the quadratic equation. Okay, so uh, sorry, let's try to hide this one. Since this is a one-to-one based on the graph, and as I've told you, you can the by using the horizontal line test, you cannot use it as a proof that the what do you call this one, that the you cannot use it as a proof or in the solution that the given is a one-to-one function, uh, meaning to say that you have to use the definition. Okay, so let's plug in. Remember that our x here is what we are going to replace. So if we replace our object here by x, then this is 3x plus 2, 2x plus 5. Here we use y, so this will become 3y plus 2 over 2x plus 5. Okay, so cross multiply. So if you are going to cross multiply, so this will become 3x plus 2, 2x plus 5, 3y plus 2, 2x plus 5. Distribute. This one is use FOIL method, or you can use your special product. Okay, we have 6x squared. The middle term is 4 plus 4x plus 15. We have 19x. Last term is 10. Also here we have, no, I guess I made a mistake again here. This should be 2y plus 5. I'm sleepy. 6y squared plus 4, 15, so 19y plus 10. Okay, so what will happen here, it comes 0. So oh, so this must be, I think I am sleepy. This must be y. Okay, this must be y. This must be y also. Sorry. So let's not erase that one. This must be y. Am I correct? Cross multiply. This must be y. Let's use another color. Cross multiply 3x plus 2 and then 2x plus 5. Okay, so here this must be y. So meaning to say this is 3x plus 2 times this one, but this one is 3y plus 2, this is 2x plus 5. Okay, this must be x, 2x plus 5. And then this must be 6xy. So I guess we have to erase this. What happened? Let's wait again for the program to respond. Okay. Also this one. Okay, wait, just wait. Please wait. Wait. What happened? Let's wait for the program to respond. This one. So this is 6xy. The middle term is, sorry, we have different variable. This is crazy. I made a lot of mistake. This is probably because I'm too sleepy now. Okay, I hope you understand. Let's just wait. Let's wait for the program to respond. We have 15x, and here we have 4y plus 10. This one is 6xy, and then 15y, and then 4x. Okay, so here we have 6xy, 6 minus 6xy is 0, and here 10 minus 10 is 0 also. So we have to transpose our x here, something here, 15 x minus 4x, and here we have 15y, this one minus 4y, and then 15 minus 4 is 11, and then 11y. So from here, is this clear? I think I am smiling, so this is clear now. We have x is equal to y. So clearly, this implies that finally h is 1 to 1. Therefore, to find the inverse, as I've said, you have to interchange the rule of x and y, then solve for y in terms of x. So first is copy the problem. So our problem is this one, 3x plus 2 over 2x plus 5. Copy the problem. Okay. Copy the problem, and then replace our h of x. By definition, this is our y. What happened? I feel sleepy. So y is equal to 3x plus 2 over 2x plus 5. Then cross multiply. We have 2x plus 5 times y is equal to 3x plus 2. This is over 1. No, this is because I'm too sleepy. First is, can I use the back option? After this is interchange the rule of x and y. So we have x, no, okay, let's wait for the program to respond. From here you have to interchange 3y plus 2 over 2y plus 5. So from here is interchange the rule of x and y. Okay, did I write the correct spelling for the rule? Is that the correct spelling for the rule? Okay, sorry, I have to use my dictionary. Okay, here, yes, this is the correct spelling. I guess what I write above, where are you? Is it RU, RULO, RULE, or ROLE? I guess I made a mistake. This happens because, okay, I made a mistake. This must be O. Okay, rule. Let's go back to the problem. Okay, interchange the rule of x and y, then solve for y in terms of x. Let's have a color blue. Cross multiply x 2y plus 5, 3y plus 2. This is over 1. So here we have 2xy plus 5x, 3y plus 2. So solve for y in terms of x. 2 minus 5x. Factor out 2x minus 3. And then 2 minus 5x. Divide both sides by 2x minus 3. So y is equal to 2 minus 5x over 2x minus 3. Finally, we are done. Okay. So what happened? This is our h inverse of x. 2 minus 5x over 2x minus 3. Okay, so uh, one of the property, okay, note, one of the properties of the inverse of a function is that the the domain the domain of the function, if the function is f defined by f, is equal to the range of the f inverse, and the let's not put a, and the range of the function is equal to the domain of the f inverse. That is the one of the property of the inverses, okay, of the functions, if you have a function. Okay, so since the domain is, since the domain is this domain of the function here before is the set of all real numbers, am I right? The domain of f inverse is the, no, this is not correct. The domain of f inverse, sorry, back, the domain of f inverse is the range, uh, the range of the, what they call this one, the range of the original function. Okay, range of the original function, we have to erase this one, and the range of f inverse, the range of f inverse is the domain of the function. Okay, okay, that would be the correct one. Why? The domain here is except the domain here is except 3 hubs. Okay, so the domain of the f inverse equal to 0 transfer, okay, that's the correct one. Okay, so please take note of this property. Okay, so you can verify that. So there are lots of what they call this one, questions, problems in the module. Okay, but before I am going to say goodbye, I will make a solution to the, I will post it later. After studying this lecture video, I will make a solution to the problems in the module. I will explain all those problems that was posted in our Google, in the Google Classroom. Okay, so please wait for that. And before I finally go, uh, please don't forget to subscribe to my channel by clicking that uh, subscribe button, and of course that small bell button for the instant notification. If I am going to upload a video, then you will be instantly uh, reminded that I have uploaded a video. So that's the purpose of the bell button. So thank you so much for watching. If you have questions, please comment in the section below. God bless everyone. Thank you so much for watching. Thank you so much for your patience thank you for being with me in this whole lecture. It's sorry, it's lag. The program is not working well, so I hope you are patient enough to wait. Okay, this is a long video. I have to divide this into two. Okay, so God bless everyone.